Hello. What I really want to talk about is differentiation. Remember, in arithmetic there are the four operations: add, subtract, multiply, divide. And I'll give you an example of differentiation. Differentiation is another operation that you do much later. So for instance, if you have 3x to the power 4 with y equals 3x to the power 4, when you differentiate this you get dy by dx, it's a funny thing, isn't it, equals 4 times 3 is 12 x, and then you take 1 off this 4 and you get 3. So if you differentiate this you get this. But you're not ready for this, so I'm going to talk about something else. I'll tell you about that later. I'm going to tell you about something about things called matrices. Nothing to do with the film. Matrix. One matrix, two matrices. And a matrix can be something like this: 0, 1, 2, 3. So this is a matrix with 2 columns and 2 rows. You might get a different sort of matrix with three columns and 3 rows, where each of these represents some number. So in this one there are 4 numbers in 2 rows. And I'm going to show you how these are multiplied. And at the end I'll tell you why I'm showing you this, not until the end. So say we have 0, 1, 2, 3, and we multiply it by, I don't know, 2, 3, 5, 4. And what you do, it seems a bit odd, it's a bit of a funny thing, but there is a reason why it's done this way. Very good reason why it's done this way. So really this is just, this thing is a helpful way of doing something which I'll talk about later. 0 times 2 plus 1 times 5. So here we're going to get this thing: 0 times 2 plus 1 times 5. We've not got enough room there. And the next one is, so when you do this, look, the top left of the multiplied one is where these two, so this is the first column and this is the first row. This is the first column and the first row. Right. So the next one, 0 times 3 plus 1 times 4. And then the bottom row. 2 times 2 plus 3 times 5. And the last one is 2 times 3 plus 3 times 4. So we start off with, in this case, I'm starting off with a matrix which has two columns and 2 rows, times another one with 2 columns and 2 rows, and that's what we're ending up with here. This is equal to 5. 4, I think. 3, that's 4 plus 15 is 19. And there's 6 and 12 is 18, I think. So this times this, the answer is this thing. Okay. And where this thing is useful, I'll now tell you why this multiplying, how it comes about, why it's used. If we have, say, a coordinate system, this is, where there's an x and this is y, and here's some numbers, look, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3. Right. Now a point in here, any point on this plane, this can be specified using 2 numbers, and so for example, this point here would be, we'd write as 1, 2, 3, 4, 5, comma 3. And you can do this with any point on the plane. And we can, what's known as, transform this point. I'm going to make it a bit easier for myself here. I'm going to choose this point instead, right? Because I've already done that as preparation. Yeah. So that point is 3, 2. That's 3 along. You always do it. This is always the x1, and then the second one is the y. Can you see that? I think you can. There's a 2 there. And we can, do you remember the other day I told you about using a machine to, we made a machine, we talked about addition or operation, these operations of, well, I think I had something like 2 times in a box. No, it was actually 2 plus, wasn't it? I remember now. It was 2 plus. We had a machine which was 2 plus, and we fed in the numbers x into it, and out comes the machine we get x plus 2. So you feed in all the numbers x and you get all the numbers out of this machine, all the numbers x plus 2. This is an operation. So this operation, I'm going to do an operation on here, on this point, and move and so that it maps to another point, so that the machine gives us another point. And a matrix is that kind of machine. So here we are. I'm going to use the matrix 0, 1, minus 1, 0. This thing I'm going to write as a column like this. I want to try and slow down a bit because this is all very fast for you, I think. This is the matrix, and this is what we call a vector, a column vector. And when I multiply this, or when I use this acting on this vector, this is what we get. I've put the vector in square brackets. Not everybody does that. A lot of people use rounded brackets, but I just like to use square brackets for vectors. So here's the vector. So operating this, multiplying this on this vector, we get another vector. Remember, here we multiply a matrix, apply a matrix to another matrix, and we end up with another matrix. But here I'm going to use this as an operator to map this point to another point, and that other point is basically a vector. A vector will often be drawn like this as an arrow. So the vector is to that point. And I appreciate this is all very fast, but I think the detail of this is not so important to remember. I just like to. I'm heading for something that I think you'll find interesting at the end. So here we go. 0 times 3 plus 1 times 2. So that's a 2. Minus 3 times 0 plus 0. Minus 3. So that's a minus 3. So the new point is this 2, minus 3, which is that far out and that far down. It's there. So this matrix has moved this vector to down there. What is it? 2 comma minus 3. Remember that the first one is always the x along, the amount along, and the second one is always the amount up or down. So this matrix has moved or mapped this point to this one. But now I'm going to start with this one and use another matrix acting on this, and that new one, that new matrix is going to be 0, 2. I'm just choosing these as simple examples. There's nothing special about them. Wait, have I done the right thing? Yeah, acting on so this new vector. So this one will map that one to another place somewhere. So that's 0 plus minus 3. Wait, 0 plus, sorry, minus 6. Is that right? Is that what I want? Not really. Am I gone wrong? I did it wrong here. No. Ah, that's why. That's wrong. That's not what it was at all. It was 2, 0, 0, 1. So the new vector here is 4 and minus 3. And so over on here, so over here this is 4 out and minus 3 down. So it's actually here in where this, this is in the way now. It's 3 out, what was it? 4 out, 4 out, 1, 2, 3, 4, and 3 down. It's there. So it's the new vector is this one here. I think I should have drawn this much bigger. But anyway. So what I did here, I used this matrix acting on this vector, this point, and it gave us this new place, this one. And then I used that, I acted on that with this new matrix to give this third point. Right. So I did two things. I did one and then the other. So what I want to, instead of doing it that way, I'm going to, first of all, what I'm going to do is multiply these two matrices by one another. I think that's the wrong order. That is the wrong order. The second one comes first. Pretty sure of that. The second one comes first. And this matrix, these two matrices multiplied, we get this. 0, 0, 2, minus 1, 0. Is that what I get before? I think so. Righto. And now I'm going to take this matrix, this third matrix, and multiply and use it on the original vector. The first point. That's equal to 0 minus 6 I think I've gone wrong. Where have I gone wrong? I think I'm going to have to throw all this away. Ah, sorry. I see what I've done wrong. That wasn't the original vector at all. This is the original vector. Right? 3, 2, wasn't it? And when we multiply this against this original vector, 0, 4, minus 3, minus 3. It's the same, look, as this. So, can you see how what I did up here was I first of all mapped this point to that using one matrix, then I mapped that point to this using a second matrix, and then just now what I've done is multiply this first and second matrix in order to get a new matrix, this one, and then that new matrix I've used on the original vector here, and in one step I get, instead of going from here to here and then from here to here, multiplying those matrices, I go directly to this one. So the important point I'm trying to show you is this thing, this multiplying the matrices. And so I've taken this was the first matrix, remember? The first one goes here, and then in front of that goes the second matrix to give us this one, this product matrix. What happens if I multiply them in the wrong order, in the other order? Naught, minus 2, naught, no, 1, 1, yeah, naught, naught. So if I multiply these in the other order, in the opposite order, I get something else. Now if I use that something else on the original vector, that equals a new vector. This is not right. 0, 2, minus 3, minus 6, and that. So that would be different from what we got when we multiplied them in the first way round. And this is the point of what I'm trying to show you. When you multiply matrices together, the order matters. This is where I was trying to get to with the whole thing. So in the algebra of matrices, the order of multiplication matters. The order of addition doesn't. Because if we add these together, we get 2, 4, we get 2, 4, 7, 7. And that doesn't matter which comes first. But when we multiply them, the order does matter. So in the algebra of matrices, the order matters, whereas in the algebra of numbers, order of multiplication doesn't matter. So for instance, in numbers, 5 times 4 equals 20, and that's the same as 4 times 5. So in one of the characteristics about numbers, I mean, I know there's numbers in here, but it's not just, it's the order of the numbers. It's a matrix that has this specific arrangement of numbers. And so what I was trying to emphasize is that when you start doing algebra at school, you very much take for granted the idea that algebra is about doing things with letters, and in the same way as you would do things with numbers. But what I'm trying to get here is that there are other algebras which you won't come across, particularly at school. There are other algebras that people study, and this algebra of 2 by 2. This is a 2 by 2 matrix. Of 2 by 2 matrices, the algebra of 2 by 2 matrices, in that algebra, order of multiplication matters. Okay. Dankeschön.